Welcome to this comprehensive video course on Memcached, an in-memory caching system known for its simplicity and effectiveness in reducing database load. In this course, Hussein will teach you about Memcached architecture and design choices, and he'll conclude with a hands-on demo using Docker and Telnet. Get ready to deepen your understanding of this transient cache system.
Memcached is a simple in-memory key value store written in C. It was originally, I think, written in Perl and then rewritten in C. This is back in 2003, so it's been a while. And it has been popular with companies such as Facebook, Netflix, Wikipedia. Facebook, I think, pushed it to its limit, And the reason it's why popular is because of its simplicity. And we're going to talk about that. I know we throw the word simple a lot these days, but Memcached is truly simple. I mean, if you're looking for advanced features, it's not here. It was designed to be simple, solve the problems of the web back in 2003, which is we want to help alleviate the queries to the database. The databases are taking a hit, So let's cache things. Although I usually do not agree with having a cache to solve a slow query, because personally, I think it's a cop-out, to just add a cache when you have a slow query. You have to understand why it's slow. You have to understand why it exactly is taking time, why there are a lot of logic reads, and how to minimize it. And that's another story for another day. But sometimes you need a cache, of course, right? And then Memcached was born, right? Of course, there are alternatives such as Redis. I made a video about it, but this video is a crash course of Memcached. We're going to dive into the agenda here. You're watching this on YouTube. There will be chapters where you can jump into the interesting part of the things, but it's an in-memory database. We're going to talk about memory management. You might say, why? Well, we're going to find out. Memory management's not easy at all. It's not just like, hey, just throw things in memory and then read it. It's a little bit more complicated than that. We're going to talk about the LRU, the least recently used, which was designed to avoid growing the memory of this instance unlimitedly, right? Because you have to have some sort of a mechanism to evict all the entries that has been never used. That's why you cannot really rely on Memcached to have a value always there. It was never the goal of this cache, right? Unlike Redis. Redis, if you start something, it's going to be there, and you told it to be there forever, it's going to stay forever. It will make sure to stay forever. Memcached does not guarantee that. And you can argue that this is actually a feature, and you can argue that this is something you don't want, so tread lightly. Thread, we're going to talk about the threading model, because you have to have multiple threads if you want to serve a lot of clients with a lot of TCP connection connected to this thing. Read and write, we're going to go through examples of a read, example with a write, and gonna open the hood and look what is inside this beautiful thing. Locking model, obviously, two people trying to write into the same item. It's not as advanced as ACID, obviously, where you have isolation levels. No, it's a serialized model where we try not to have two people read the same item at the same time or write the same item at the same time. So locking. And we're going to talk about the old model and the new model. That's where you really try to understand how things are built is completely different from the way we explain it. Distributed cache, I know they say it's a distributed cache, but I kind of don't like to say that, because in itself, Memcached is not distributed. It's just when you spin up a Memcached instance, 3 Memcached instances, they don't know about each other, and they will never be. Right? The client is responsible for the distribution. So I kind of reluctant to say it's a distributed cache. I know people call it a distributed cache. I don't like to do that. But hey, it is a distributed cache if you put the distribution at the client side. And I think this is part of the beautiful, simple design. They on purpose, they didn't make it distributed to make it simple. And then we're going to go through a demo. we're going to use Docker because you can spin up a lot of instances in Docker really easily. Let's do that. So, in-memory key value store, what's that really? We're going to talk about some terminology here specific to Memcached. An item, that's what they call it. An item is really what consists of a key and a value. A key is usually should be unique, right? And a value could be literally anything. A key has to be a string, and it maxed out at 250 character. You can see the limits, right? That's why I think Redis kind of won the cache game when it comes to this thing, because Memcached has a lot of limits, and this kind of crippled some people from using this cache because of these limits, right? But you can argue also the simplicity of this design, and if you can work around the design to use Memcached, it's actually pretty nice, right? When they take key as a string, they did that for a simplicity reason, right? If you support like dates or I don't know, like blobs as keys, then things become really complicated, and that shows in the architecture. And if there is a bug, it's really hard to track down, right? And the value can be any type. It's by default 1 megabyte. Again, another limitation in Memcached. You can see that I talk about limitation, but these limitations technically, to me, I see them as features, because they didn't claim to be like the best in the world. They said, hey, we are designed to be simple, and I appreciate and I completely love that. When you say I want to build something simple, the simple thing has limitations, right? The simple thing will, by design, have limitation when you look at the big picture, right? It's not going to have like tons of features, right? So yeah, you can configure this to increase it. But again, it's not really a good idea all the time. Keys have expiration date, TTLs, right? Time to lives. And even that, don't rely on that, right? Even if you put like a key that has like a 1 hour, and your memory is filled, the LRU can kick in, and if you never use that key, it's gonna get affected. And they tell you that, right? Hey, Memcached is a transient. We're not gonna make sure that it's actually persisted. It's not supposed to be that, right? Again, we'll always go back to the requirements here. They never meant, right, for this to be a persisted cache forever, right? You don't rely on that. You can use it to help you avoid expensive queries. But yeah, be ready at any time that this value is not going to be there. Everything is stored in memory, right? That's by design. Memcached. Again, don't confuse Memcached with Memcached DB. That's a completely different project, and I think it's abandoned since 2009, right? But yeah, Memcached is still going, and Facebook, and I think Mark Zuckerberg gave a presentation about Memcached as well as at some point, how they tuned it to its maximal values. Let's talk about memory management. Here's the memory, right? When you allocate items, when you say, hey, I want to allocate an array, and I want to allocate an integer, and I want to allocate, here's a block of memory, these items that you allocate, and even in your program today, they're going to go in random places. Now, yes, the process has a dedicated memory area, but when you allocate, these things go random. So the grain is allocated, they're going to go to random places, right? Yeah, initially they might be consequent, but as you remove and free items, you're going to end up with these gaps. So you might say, what's wrong with these gaps? The problem is this is called the fragmentation. What's wrong with fragmentation? Well, you're going to have like a little bit, a few bytes here, a few bytes here, a few bytes here, a few bytes here. But if you want like a big bulk of memory location consequent, like you want 1 meg, you have 1 meg, but it's fragmented. And guess what? If it's fragmented, you cannot use it. You cannot just allocate here, my part, and then this part here, and this part here. I think that the operating system allows you to do that, maybe, but then it will thrash left and right to collect what you have, right? We had the same problem with hard drive, I guess, right? Back in the days with fragmentation, where the seek, the needle has to go multiple places to fetch your files because it's a circle, right? This disk, and has if you store a file and you start editing the files will go to multiple sectors, and to read that file back, you have to go sector 1. Sector 2. This was supposed to be like a rotating disk. I failed miserably. But you get the point, right? So memory fragmentation is bad. We try to avoid it, right? New items can no longer fit. So what did they do? So Memcached, at least, what they did is they allocate pages instead, even if they don't use it. They say, hey, when you start, allocate the whole page, 1 meg. Again, that's the design, right? That's the reason why we have one value up to 1 megabyte. You cannot go beyond that. So they say, hey, let's start with the 1 meg. So if they allocate a 1 meg, the whole thing. They don't use it. Technically, to the operating system, the cache has used 1 megabyte. It doesn't know it, right? That it's not actively using it. The clients, us connecting to Memcached, we're using like part of that memory. Does that make sense? But this avoids fragmentation, right? Because now all of this is just one big page with a lot of empty space, right? But it is allocated. And then there's this idea of chunks, right? So the pages are broken down into equal size of what they call chunks. So keep these in mind, the terminology in mind. The chunk is a fixed size. And what determines the chunk size is actually something called the slab class, right? The slab is, think of a slab. Every time I hear the word slab, I remember Dark Souls, it's a video game where you have the last item that you require in order to upgrade your weapon. It's called the Titanite slab, where it's just like really large rock that you use in order to upgrade your weapon. It's basically a big thing, a slab of meat, they say, right? It's just a big thing. That's what it means. So this idea of slab and slab classes will always show up here. So it's like a big portion of memory. A slab class is what defines the chunk size, right? So there will be a slab class of 40 bytes. There will be a slab class of a 1 meg. So the chunk sizes will be 44 bytes, right? And the chunk sizes for a slab class of that type is 1 meg. So we're going to show an example to show that of stuff. And the pages consist of fixed chunk size, right? Items are stored in chunks. Here's the very important item. So your item will be stored in the chunk. Your chunk size can be, let's say, 100 bytes, right? If it's 100 bytes and your item, which includes the key and the value, is less than 100, you're going to include the whole chunk, right? So if it's 90 bytes, you lost 10 bytes within that chunk. Nothing to do about it. Sorry, right? That's one limitation here. So there will be a free space, a tiny free space in the chunk. And obviously, each slab class has a fixed chunk size. So that's how they are determined. It's going to be clear as we go through that. Obviously, avoid memory fragmentation. Here's an example, right? So here we have a slab class with a chunk size of 72 and subclass 1. And slab class 43, for example, the chunk size is 1 meg. So you have in a single page, right? So slab class have multiple pages. And sometimes they call them also these called slabs. The word slab in the documentation is so overloaded, and I've seen people use it one over the other, so I avoid using it, the word slab. So a slab class, and their pages, right? So this page, in this case, we said 1 meg, right? And the chunk size 72 divided, that means we have 14,563 chunks per page, but each chunk is 72 byte, right? So if you have an item around 72 byte, fits nicely in this. Okay. But if your item is larger, let's say 900K, then, it doesn't fit this slab class. So we need to, let's find out what is the subclass for this item. Subclass 43, because the closest 1 meg. And guess what? The 1 meg class, slab class, has this entire page is 1 chunk, right? So this is really important to understand here, right? So that's how they allocate memories. We're looking at the internal architecture of Memcached here. Right? Let's go run an example. New item, 40 byte. 40 byte. The closest thing is this guy, right? Slab class 1. Let's allocate memory, and then boom. No, we don't allocate memory. This memory is already allocated, right? We just store the item right in this chunk, and then we start adding pointers and stuff like that here. So now our item is right here. And we're going to talk about the hash table and stuff like that, but this is just, again, memory management. Let's say I have a new item, 900K. Oh, this fits right here. So one big chunk in one page, right? So that's interesting. Let's say a new item, 40 byte, but guess what? Slab class 1, because that's what the chunk size is, fits it nicely. But guess what? We have 2 pages. They're all completely full. So I cannot insert this. What do? Create a brand new page, put that thing here. Does that make sense? So we allocate a new page. And when you go to the demo, we're going to see all this stuff, right? We're going to do a stats and see like, oh, how number of pages allocated is this, right? So it's just, I absolutely love how they did this. It's interesting. Obviously, does it have limitation? Of course. But you're going to see that depends on the sizes of the item, you say. And once you really understand how things work, you can architect your application, specifically the backend here. Frontend doesn't really talk to Memcached at all, right? The backend here can be architected so that you can choose the perfect items, right, to fit this entire thing, right? You're not gonna just choose haphazardly, right? That's how you know your craft effectively. All right, let's get to the meat. LRU. Least recently used. The main problem with memory is it's limited. And even if Memcached allocated a certain amount of memory, if you store a lot of keys, even with good expiration date, memory can get full. What do? Do you block new inserts? I would say that's one feature that you can add, I suppose. But Memcached don't allow you to do. They won't let you go to that state. If the memory is about to be full, then anything that hasn't been used for a very long time, they will release it. That's another reason where Memcached is a transient memory. It do not rely on a key. Even if you set the expiry for an hour, do not rely to that key to be there in an hour. It can go anytime, right? That's another limitation. That's another feature, right? I say limitation and a feature at the same time because it is a feature, right? And it's to some people it's a limitation. And how do they do that, right? They use something called the linked list. Have you ever heard about this before? 21 years ago, in the university, I took a course on the CS 101. They talked about linked list, and that is pretty much the only time in my entire professional career I ever used a linked list. That's probably, I'm not saying that's just the case with the application I wrote is all high level languages. I never had to write a database or a memcache, so I never used the linked list, right? So doesn't mean that it's a useless structure, but it is. It's an important data structure. Why? Because the least recently used is a linked list. There is a head and there's a tail, and every item is linked to each other. So if all these items that you add are in this architecture, right? They are in the linked list, and every slab class has its own LRU, right? So if I, for example, access an item that happens to be in the tail, it will be popped and go back to the head. So there is a cost to accessing an item. There is a cost. There is a cost of removing this chain, putting that back, pulling the head to this, pulling this guy to this guy, pulling this guy to this guy. That's how you do a linked list, right? So every time you access an item, it goes back to the head. So items that are not used, they will automatically be pushed down to the tail. And if the memory is out of reach, basically, these items will be removed from the tail. But also another thing with this linked list is like with threads, which Memcached is a multi-threaded app. How can you have multiple threads read at the same items, right? You can't. You have to lock this structure. If people who done multi-threading, you have to lock it, right? And the moment you do locking, if you know about something about databases, which I teach a course on database engineering, check it out. It's actually right here. database.husseinnasser.com. I talk about all this stuff, in details, in fundamental details. So don't expect like SQL syntaxes in my courses, not like that. Right? I talk about fundamentals, which you then build up and see how the client is built out. Right. But yeah, locks is a very critical concept here. You have to lock it to avoid this, mutation, corruption, right? But yeah, it's a cost. And there's an LRU crawler and a daemon that does the cache eviction from the tail, right? And again, every time it kicks out, have to lock. And if it's locked, people cannot read. Threads cannot read. And if threads cannot read, latency, right? Block, slow, right? All of this, you gotta understand when things happen, this is why. And I'm gonna share my opinion about the LRU, right? And I think this is a good time. By the way, there is an LRU cache per slab class. I think I mentioned that. So the 1 meg slab class, right, which has like pages of 1 meg and the chunk sizes of 1 meg, has its own LRU, and each other slab class has its own LRU. By the way, I'm not making any of this up. I had to read, frankly, maybe 20 different documents to collect this information and kind of present it in a summarized manner here, right? Because there is no one doc to explain all that, unfortunately, right? It's not incomplete, unfortunately. That's what I noticed. And outdated. So my opinion about the LRU, in my personal humble opinion, is I wish Memcached actually disabled this by default. LRU is a feature, right? And the reason they added it, because memory is limited, especially back in 2003 when they first built this thing. Memory was so scarce or scarce. Is it scarce or scarce? Scarce, right? It's very limited. And when you do that, you don't want to run out of memory, right? So if you allocate certain amount of memory for Memcached, it can easily run out, right? If you have a lot of keys. So how do you manage that? They say, hey, we're going to build an LRU. Least recently items get kicked out from the memory. That's a fine, but I wish they disabled that by default or give us an option to disable it, because the overhead of managing an LRU, and you can see from the papers I'm going to reference, is so large. The locks that they have to maintain slows down throughput, right? And complicate the application. So I think they stuck. Whoever built this in 2003, Memcached, Brad Fitzpatrick, who is the original developer of Memcached, he built this for his website LiveJournal. I wish he disabled this by default. I really wish, because his original design is so simple and so elegant. I absolutely love it. You build something so simple with its features stripped. There are no much features. LRU made it not simple, unfortunately. Yeah, cool. Have a feature, but disable by default. Or have an option to disable. I don't know if there's an option to disable. Maybe there is. But hey, I want to take the responsibility as a client, right? If I'm going to allocate certain amount of memory because I'm responsible, I'm going to give Memcached 5 gig, 10 gig, and my application is smart enough to know to set expiry date, right? For this item. And yeah, if I'm going to get errors, if it's filled out, it's on me. I want to delete 10 items. I want to do this management. This way, for 95% of the users who want simple things, they're going to get it. LRU, in my personal opinion, again, this is just my personal opinion. You can agree or disagree. I think this should have been disabled, because now they created a new LRU which is like has hot and warm and cold and they move stuff around because they have a lot of problems with LRU. Like moving stuff around all the time is so expensive, So it has a cost. So let us just, how about give me an option not to use it and go back to a simple model. Of course, I don't mind if two users try to access the same, two threads trying to access the same item at the same time. Let them be serialized. That's fine, right? But LRU as a whole thing, I think is just, to me, over engineering. That's just my opinion. You can disagree. Here is how it looks like, by the way, LRU in the big picture. Again, this is all drawings. I made it. I could be wrong in small details because I don't know the actual architecture. So I derived these from reading the source code and the doc. So this is how it looks like. So this is where you talk about the pages, right? And the chunks. So the chunks or the items is what being LRU'd, right? So the head is right here, and this is linked to this item, this is linked to this item, this is linked to this item, this is linked to that. This is the tail. So this is how it looks like. Every item here is actually linked to the one next to it, right? Think of this as a snapshot after many usages, right? Gets and read, so things will move to the head and the tail. Obviously, I didn't draw every particular thing because it's gonna be a mess of a drawing, but you get the point, right? That's how the LRU, and you can see how complex things get. So let's talk about threading. So this is one of my favorite parts. I know I absolutely love networking, and if you're interested, I have a networking course, and this part is all about sockets, connections, the way listeners work, the way the TCP connection works. I talk about this in detail in my network course. So if you're interested, go to network.husseinnasser.com, learn more about that. Again, network.husseinnasser.com. This URL redirects immediately to Udemy with the latest coupon applied. So you're going to get a discount and you're going to be supporting this channel, this work. Thank you so much. Here's the threading model for Memcached, right? Because it accepts clients, it has to have networking, right? So what they do is they listen on a TCP port, right? So that means they support transmission control protocol. That's the native transport that they support. They also support UDP, which I didn't mention here, but UDP has been now disabled by default because of an attack that happened 4 years ago, 2018, a reflection attack actually, right? With Memcached public servers. So there was the Cloudflare actually reported that. So UDP has been disabled by default, but yeah, you can use it if you want. But yeah, let's stick with TCP right now. TCP port 112.1.1, and there is a listener thread. So one spin up listener, one thread that spins up, it listens to port 112.1.1. So that creates a socket, right, in the operating system speak, right? And that basically creates its own accept queue, its own send queue. This is how the applications start accepting connection, right? So every single connection that is happening, the listener thread will accept it. So there is a loop, infinite loop here. Literally all application has this loop where it's constantly accepting connections. One thread, right? So all the connections goes to this thread. So once it accepts the connection, it gets the file descriptor, we call it, right? Which actually represents the connection. And now what Memcached does is spins up a new thread, gives that file descriptor to that thread. Now, if a stream of data, if a request to get a key was sent to this connection, the operating system knows to send it to this thread. Well, technically what happens is the thread polls the file descriptor, right? This thread is responsible for this connection. This thread is responsible for this connection. This thread is responsible for this connection. So you can see that now this model just blows up, right? If one connection per thread, if you have so many connections, you can run out of threads, right? Or that kind of also bloats your memory and CPU. So be careful with that as well. Right? I think they put a limit to the number of connections, Memcached. I might be wrong there. But yeah, so this is basically explains all of that. Now, the moment you have threading, now the beauty here is you don't have bottleneck, right? If you have one thread that is responsible for all the connections and listening, you will be blocked, right? One user will send a key and then another user will send a key. They won't be served, right? They have to be serialized because there is one thread actually executing them one by one, right? But here, if one user sends a key request to get a key, and this guy wants to write, they can happen at the same time, right? This thread will read it, and this thread will read it. They are different processing. This could be in a core. This could be in a completely different core. That could be also possible. Versus it's one thread, then becomes really a problem. So we had to go with multi-threads. What's the problem with that? Well, the problem is these threads will try to access what we call the LRU and the items and the memory. So everything is shared between all these threads, but you can't have two threads write to the same location. That's a problem. That's why the original design had one global lock. It was serialized. So in this case, yeah, the threads kind of helped with the connection, but you were serialized at the locking model. So nobody can even access two different items. Has nothing to do with each other. They were serialized. They were locked. So one thread has to be served after the other. They fixed that. They completely revamped that. Now it's a pair item lock. So if two threads try to access the same item, then it'll be serialized. That's good. That's okay. I'm okay with that, right? But yeah, if I'm accessing item 1, key number 1, and then another thread access key number 2 at the same time, they should be served at the same time. There is no reason for locking. And the only reason we lock is because we want to update the LRU. Again, so there is so much stuff that comes back always to the LRU. It's like, oh, really? Did we really need an LRU? Why? What if we disabled by default, right? Again, that's just me. Let's go through an example. A read. And this is something we never talked about here, which is the hash table. If you think about it, if you have a key, how do you actually find where this key lives, right? If you think about it, you need hash tables. Yeah? So what you do, and I talked about the hash table in my YouTube channel, look up hashing and consistent hashing. I talk about details. Hash table is nothing but an associative array. It's really just an array. And the beauty of an array is, if you have an array, right? Let's talk about arrays a little bit. If you have an array has to be consecutive. If you allocate an array of 1,000 elements, accessing element number 7, accessing element number 1024 or 1033 is big O of 1, is fast because you know the index. And once you know the index, and you know the head of the array, you add the address to the index, voila, you have the address and the memory, the CPU can immediately go to that location. That's the beauty. You have an index. With hash tables, you don't have an index, you have a key. The trick is to convert the key back to an index. That is all what it is, a hash table. Nothing fancy, it's just an array. So we take that, what we do is do a hash on the key, right? Let's say I'm gonna read test key, right? And then do a hash, and then do modulo n, where n is the size of this array or the hash table, right? And then you're gonna get a value between 0 and n minus 1, I guess, right? So now, okay, let's go on, point it, and that's big O of 1, plus the cost of the hash, right? Now you got here, found it. Now what you do is you're gonna get a pointer which takes you to the page on that specific slab class for that item, which is happened to be D in this case. That's how a read works. So it's a big O of 1. You can argue that this is one read and this is a second read. Yeah, I suppose that works too, right? I think the new model have kind of 2 hash tables, if I'm mistaken, but I couldn't find detailed docs about this, so I explained this. So apologies if this is a little bit out of date, but this gives you the idea here. The new 2 hashes, I think they were provided to provide a pair item lock. And obviously, what happened here is, this is the LRU. You access the item, the D is pushed to the head, right? So now you have A, B, C, D. A is now the least recently used item, is in the tail. And A points to B points to C points to D, and obviously it's a reverse linked as well. So D points to C points to B points to A, right? So that's how the LRU. Actually, if you think about it, the pointers are right here in the item itself, right? But I drew it this way for simplicity, otherwise it's not readable at all. Read 2. This is another example of a read. I'm gonna read buzz, hash the buzz, get the N, whoa, get the item, boop, get a C. Nice. Now when we read a C, the C is pushed to the head, D is slightly pushed, and then obviously the LRU is updated. And that's another lock, right? You have to do a lock to do that. So if buzz and whatever the value before a test was read at the same time, they are serialized at the LRU level if they belong to the same slab class. Again, this might have changed with the new architecture. They changed that a little bit. So I think that you can you can play with that a little bit. But again, to update the LRU, you have to kind of acquire a lock. So you're going to be serialized right here. Yeah? Let's go through a write. I'm going to write key new of a value with 44 whopping bytes. Let's do that. Well, to write, we need to obviously find the hash, right? Where to write it. Hash modulo in, get that puppy, find where to write it. Oh, happen to be an empty location. Sure, that's good, right? And now you have questions. What if I happen to have something that is already written? You can have collisions, and we're going to talk about collisions in a minute, right? It's a problem of hash tables. Hash tables are fun and good, but the moment you run into collisions and you want to resize it, it falls apart. But now I create a new pointer, this pointer. Now I need to allocate a slab class, not slab class. I need to allocate a chunk where I'm going to put my item in, and that chunk goes into a specific slab class. Well, 44 bytes, pick a slab class, right? And even the slab classes, guys, by the way, it's not really fixed. You can play with those. The other configuration called the chunk factor growth size. I'm not going to mention it here. It's just going to make the course a little bit longer, but you get the point. There are so many tweaking you can play with, right? Tweak these chunk sizes. But yeah, allocate a new memory location in this specific page, in an empty page, in a fitting chunk, right? Because you want to pick a chunk that is almost fits right in the chunk, right? Not too small, obviously cannot be larger than the chunk size, have to fit right into it, right? But that's what Memcached does. All right, let's spice things up. Let's say I'm gonna write a key called nanny, which is a new key. I don't have it before, and value 44, but it happened to clash with another existing key, because hashes always do that, right? So when you do that, you hash nanny and happen to be fitting on a entry that already have a pointer. What do? Do we overwrite it? No. What they did is, this is called a bucket, by the way, right? They add more item to the bucket. We have one item, let's call it, I don't know, test or something, all right? And then we have nanny, which fits right in the same bucket. What we do is we make it into a chain, this chain of buckets, right? Actually, one bucket with 2 items, I don't know, right? Whatever the terminology, doesn't really matter. You just read to understand. Let's turn back the laser here. And yeah, we're going to add it here, and then just do the pointer and do your thing. Now, obviously, we need to talk about a collision. What happened to a collision? I want to read the key nanny, right? Go here, hash it, obviously go here. Oh, we have 2. Which one? That's the cost. You have to go one by one through all of them, right? Why? Because now you have a hash. You don't know which one of these are actually nanny. What you do is read the first one, right? Check it, compare the key. Oh, because if you go to the item, you're going to find the actual key, right? That's stored here. So you're going to find it and say, oh, that's not nanny, that's something else, right? Let's go through the bucket. Go to the next one. There you go. That's my item. So here is a completely different paper that you can write here. People take PhDs in this stuff, by the way, guys. This is called the scale factor. Memcached measures this growth, and if it's too much based on a certain percentage, if you're overloading, then you're gonna see performance problems, right? Reading a key is gonna have to go through multiple reads to find the actual key. Versus if it goes right here, hey, the key is right here. Of course, there's one entry. It has to be it, right? But if there's multiple, yeah, then it's a problem, right? I mean, you can think about it. You can argue that you can hash a key that happened to get to a value that is not there. So technically, you have to read it and compare, because your key might not exist, but it happened to hash to a value that it does, right? So you have to read it. So there is a cost to reading. So that's the problem of hash table. So, and if that's the case, then they do a hash resize. And boy, when you rehash your table, they have to shift everything around. And I believe this is when they use the consistent hashing, which is this ring concept, which I talked about in another video. And that just gets really complicated, right? Because they now, the moment you resize your hash table, you need to move stuff around. Because Nanny will not be this index number 1 anymore. It's going to be index number 7000, something like that, right? 7000 is not a number. I think I'm going to skip this because we talked about locking in a minute. We talked about threads and then accessing the LRU and how it was a global lock and then it changed to a per item lock. And then still we have ref counting. Every time you read an item, you increase the ref count, and when you release it, you decrement the ref count. This is so the garbage collection is written in C. There is no garbage collector, but the ephemeral application level garbage collection, when LRU kick in, can remove the item, because you cannot just remove the item if someone is referencing it. That's the definition of memory leaks, right? All right, let's talk about distributed cache and how it's Memcached is actually not a distributed cache, in my opinion. Memcached servers, when you spin up a Memcached server, they are completely isolated. You cannot link a server to another server. There is no mechanism to do that, right? When you spin up a Memcached server, it's a Memcached server. It doesn't talk to another servers. And I absolutely love this design. How simple and elegant this is. Put the responsibility. If you want to do distributed, well, the APIs at the client side has to do that. And that's what we're going to show in the code section, where we're going to write our own, we're going to use a NodeJS application to do that. Obviously, we're going to use also Telnet to connect to that and write stuff, right? But we're going to go through all this stuff now. But yeah, what happens here is the client actually knows about all the servers. It has knowledge. So the client side actually does the distribution, right? So it's like, okay, key number 1, go here. Key number 2, go here. Key number 3, go here. So there is a hashing going on, consistent hashing to be specific. You can build your own Memcached client that does whatever you want, right? And then distribute that stuff. Well, what happens if I add a server? Well, your client can start distributing the keys. I would definitely not be with that, because why would you distribute the keys in a transient cache anyway? Who cares? Add a server is like, oh yeah, if the key is not there, you're gonna query the database and pull it up, right? It's not worth it to do this chattiness to move items around from one server to another. That's just a bad idea. I don't know if clients do it. Maybe they do, but I don't think it's required. It's just thrashing for the case of thrashing. Database sharding. Again, you might, if you know this channel, you know that I tried as much as possible to push it as the last resort. I do not like distributed stuff. Especially, it's so complex to deal with, right? I like simplicity. I'm a simple man, right? But yeah, sometimes you go to the YouTube scale and Google scale, then you don't have a choice. One machine cannot possibly handle everything. I would go with RAID replicas. I would go with partitioning, horizontal partitioning in the server itself. Minimize that as much as possible. I would go with RAID, distributed disk storage, but the application remain as a single writer. The moment you have multiple writers and you have to deal with the sharding, it becomes really complex. If you want to deal with the complexity, sure. But yeah, that's the idea of distributed cache. Okay, let's do a demo. We're gonna do a demo. We're gonna spin up a bunch of Memcached Docker instances. So for this exercise, you just install Docker and you're good to go. And you have to have a Docker. You have to have a Docker account, because somehow they are locked behind an account. Memcached. I have no idea why they do that sometimes. right? So you just create an account, do a Docker login, you're good to go, right? Once you do that, you can download the image and you can spin up as many Memcached instances as you want. So we're going to do that. I'm going to use Telnet because I love the simplicity of Memcached. You know how many clients these days that you can actually just Telnet and run commands to? They can be counted on one finger, you know. They don't exist anymore. The simplicity is gone from these from today's applications, right? The good old days of you just Telnet and run. And one thing I didn't mention is Memcached doesn't have security by default. So that might be a deal breaker for you, right? So you can implement authentication, which doesn't exist by default. SSL, I believe they call it. You can implement TLS if you want, but by default, they don't have any of that stuff, right? So take it with a grain of salt, right? They said simple. It is simple, right? But you have to be careful in a cloud environment when it comes to Memcached. You have to TLS it, right? They support that. There is a support for that. And obviously, we're going to use NodeJS Memcached for this consistent hashing. And I'm going to put all our Docker containers and play with that a little bit. How about we do that? So I have Docker installed here on my Mac. You can have Windows and install Docker on top of it. You can have Linux and install Docker on top of it. That's why I always like to use Docker. It's an agnostic. Whatever your application is, you know, whatever your operating system, Docker works, you know. We have it on top of all of this stuff. So let's go ahead and spin up a Docker container that have a Memcached instance, one Memcached instance, right? So Docker run, you do -- name. Let's give it a name. Let's call it M1 Memcached or Mem1, right? You don't have to give it a name, but I like that so that we can find it and delete it later easily. And then you can expose the port by default 11211. Right, 11211. So this is what is running in the container. This is what is exposed in my host, right? Because I'm gonna hit my host, which is Hussein Mac, that's the actual host that is running Docker, and then I'm gonna hit that port, which will be port forwarded to this container, and I'm gonna spin up another one with 11211, 11212, and 11213. Right, later we're gonna spin up multiple ones. And then finally, we're going to do a Memcached, right? If you do just like that, this will block the terminal, you know, and it's going to be just work. So I suggest you do that first. I know it's going to work for me because I did it before, but I like to do -d, right? -d means just, hey, detach it because I'm going to use this terminal for something else later, right? So just like that, we created a container. You can do Docker PS to make sure that the container is running. Obviously, if the image is not there, it's going to download it for you. And you have to do Docker login to do all that stuff. So do all of that, log into your account and all that stuff. All right, so let's test it out. How do you test it? Telnet. What are we telnet into? Hussein Mac, which is my host. And which port? 11211. Again, this is the port that I exposed that happened to be the same. Doesn't have to, right? If I do that, all of a sudden, I'm logged in. How do I do that? Well, let's do a stats. Give me your stats. And this is the stuff that most of the stuff here we talked about currently, right? Uptime, what's the version of Memcached, the pointer size, maximum number of connections, 1024. We talked about that, right? There's a maximum number of connections. How many times you run a get, how many times you run a set, how many times you incremented, the threads, how many threads you have here, right? Eviction, how many times the LRU kicked in and evicted stuff. And then you can do like stats slabs, I think, which are going to give you like how many slabs were active, how many is actually allocated. Obviously, we don't have anything because we didn't do anything, right? So let's go ahead and set something. So to set a key, you do set, and then you do the key, let's call it foo, and then the flags, 0. I don't have any flags here. Flags, you can do more further controls over here. And the second parameter here is the expiration. So let's say it's 3600, which is an hour, right? You can set it for an hour, you can set it for a minute, you can set it for a second if you want, right? That's the expiration. So if your item ever get to after an hour, it will be evicted. It will not be returned to you. Not necessarily will be evicted until the LRU kicks in and that actually physically removes it, right? And then finally, we're gonna put the data length. How big is the value that you're gonna set? Let's say 2 characters here. right? So I'm gonna do hi. You have to exactly match it, right? Otherwise it's gonna be, it's not gonna fit nicely, right? So now we store the value. So let's read that value, give foo. Yay! I know this is just very simple stuff, but you get the point, right? You can increment, you can delete that key, right? And if you delete it, you can read that it's not there. So very simple stuff. I don't really care about the API. I want more to talk about the architecture of stuff here, right? And that's what matters here. There are actually two protocols, command sets. This is the old one, and there's the new one, which starts with MG, like 2 characters, and there's like a different set of syntax, right? There are 2 syntaxes here. Syntax, can you say syntaxes? I guess you do, you can. But you can play with this. It's very simple. You connect to that, and you see I didn't log in. There's no accounts or anything like that. There's no collection that you create. It's just a free floating, right? Some people might like that. Some people might not like that because they want partitioning. Hey, let me create a table or collection. Let me play with that key value right there. So it's a free for all. If I destroy this connection, so if I destroy it and I connect it again, right, and I do get foo, obviously it's not there because we deleted it. So if I set it again, flag 0, let's set it for 10 seconds or 2000 seconds, whatever. And then to hi, stored, get foo, right? If I killed it, now let's kill the session, right? Quit, and then do again, connect, and then get foo, the value is still there, obviously, right? Because it's stored in memory, right? Even if I connect it as a different TCP connection, right? And now that we did that, if we do stats slabs, you can see some interesting values that we talked about here, right? The chunk size, right? So we have this number 1, which is, this represents the slab class that we talked about, right? So we happen to have 1 slab class because my value is so tiny, right? If I create another chunk with a large value, the large item, another slab class will be created, and that will have its own configuration. So the chunks per page, which we talked about, 10,922. We have 1 page only. As we add items, we can just increase that if we want. How many is in used? 1 chunk. How many is free? 21, 10921. So that's the total. We used 1. How many time we read it? How many time we set it? How many time we deleted? Everything here is actually accounted for. Active slabs, we have 1 slab right here, effectively active. And this is the memory allocated, right? So it's like what? That's like 1 meg exactly, right? That's the meg that is allocated. We talked about that. So yeah, so you can start playing with that and add multiple data points and look at the stats and play with it a little bit. So let's control this and quit. So now that we talked about Telnet, how about we actually go to Node.js and build our beautiful, interesting application here. All right, so I created this. I went to my projects folder here. I'm gonna go ahead and create a directory called node mem, right? And I'll just go ahead and do that, right? Do an npm init-y, right? I have a Node.js, of course, installed right here to do all this stuff, right? And then let's create an index.js file. And we're going to do const memcached equal, I believe you just do require memcached, literally. And that's the library we're going to install. So once we have this library, we can call it, right? How can I call it? Const, let's call it server. And then we're going to create a new memcached. And here's the interesting thing. You can pass in an array of servers, and you can pass in a string, you can pass an array, or you can pass an object. If you pass an array, then the keys will be evenly distributed between all these instances. Today, I have only 1 server, so Hussein Mac 11211, all right? Close the array. We're going to add more servers later, but that's it, basically. Because server, I guess server pool is a better name, huh? Let's call it server pool, because that's what it is. It's a server pool here. Let's create a function called run, and this function will be called in, right? And this function, we're going to use the server pool, and we're going to set a value. So here's how you set a value. Set pool, server pool dot set, and you give it a key. Say foo, right? And then the value, bar, right? And then expiration date, an hour. And then the final one is a callback, which gives you like, in case of an error. I'm not gonna set it because I trust that it's gonna just work. So all we have to do is do that. And this will just set the value. But for the sake of time, I'm gonna actually set 10 values, 3, 4, 5, 6, 7, 8, 9. For those who know JavaScript, we can do this trick, like for each. I think you can do a better job at this than I will, but I think this works, right? this should work, right? I like that. So they will have a different key, A, and the bar will have A. This way we'll set what? 10 values in this case, and each value will have the foo A, foo 1, and bar 1. Foo 2, bar 2. The reason I do this is because I want to actually see the value. I'm not going to read it from here. All of us are going to do that is just run. And I'm going to read it from Telnet. Right? That's how I'm going to do it. Let's go ahead and do save, npm install, memcached, and then npm. That's it. Node index.js. Hopefully it runs. And of course, the moment I say that, I have an error. So let's go ahead and check the error here. So I'm going to see what the error is for each. So let's go ahead and just add that. Okay. This is going to print the error in case there is an error, just in case. All right, let's try it again. Node index.js. All right. Now it works. I had like a typo, so I had to fix, but look at this. Get foo 3, get foo 4, get foo 5. We're getting all the values. That is pretty cool, you guys, right? It's pretty cool. So here's what I'm going to do now. Let's control exit here. Quit. Here's what I'm going to do now. I'm going to spin up more containers. So it's going to do run -- name mem2, right? And they call it -p 11212 11211. Again, this is the actual port. This will not change. This is what's changing here, right here, right? Detach memcached, right? Gotta do the same thing. Port 3. That is pretty neat, right? And for sake of completeness, let's add 4 servers. Why? Servers are free. We can spin up as much as we want. Now let's edit our application right here. And what we're gonna do is literally just add a comma. Say, hey, Hussein Mac 11212 is another server, right? Here's another one too. Hussein Mac. All they are living in the same server if you think about it, right? It's just different services, right? Hussein Mac 11214. That is awesome. Nothing changes, right? So I'm gonna do it again, and then node index.js. I want you to pay attention to what will happen now. The client app now distributed all the stuff to all the servers. So now my foos will be all over the place. Let's test it out. Telnet Hussein Mac 11212, right? Let's connect to 11212, the second server, and then get foo 1. It's right there. Get foo 2, not there. Get foo 3, not, yeah, it's right there. Get foo 4, it's not there. Get it? It's because now the distribution is up to the client. I have no idea how this will be distributed. Probably round robin, but could be something else, right? So if I pick now another server, right? 3. Let's do that. Get foo 1, not there. Get foo 2, not there. Get foo 3, not there. Get foo 4, not there. Get foo 5, right there. So it took us like 5 is there, right? And you get the idea. These keys are now distributed everywhere. And when you ask about it, now I'm going physically to the server itself to ask about it. But if I ask the Node.js app, it's gonna give me these values, right? So here's what I'm gonna do next, right? I'm going to do index.js after I run all these, which is, I'm not going to run it anymore, right? Because I already store these for an hour. I'm going to just go loop and read, right? I'm going to create a function that reads. And exactly similar, YY, P. And then just do a get, right? The get is slightly different. What we're going to do is you don't need a value, right? You don't need an expiry date, but it's going to give you a function, a callback, where it's actually two places, error and data, right? And then we just print the data because that's what we're interested in. Assume there are no errors here. Again, this is a very simple app here. And then just go ahead and read. So in this case, you're talking to the pool directly. You're not talking to individual machines. So we know that the keys were actually evenly distributed between the servers because we telnetted into each servers and tested that out, right? So now what we're going to do is let's run and see node index.js. Look at beautiful. Bar 9, bar 2, bar 4, bar 3, bar 6, bar 7, bar 8, bar 1, bar 5. Why do we get the different values? It's very easy. Because we're running asynchronous job. We have no idea. Yeah, we executed foo1 first, right? But foo, right? We what we did is like we looped and sent all the 10 requests at the same time. Okay. This is what we did. We looped and sent all the 10 requests, but these are asynchronous. So bar 9. Foo9 might give us a result before Foo8, right? All of these are just, this is how Node.js works. It's single threaded and it sends all these requests and just loops through its main, the main loop, the main thread loop, right? And looks for the result. It depends on the server, how fast it's going to respond, right? So it's going to send all these things and then, hey, the server responds for this, we'll just do all this stuff. So the client here, it really depends what it does as well, right? So the client really depends on this. It took the hash, right, of the foo1, determined that foo1 should exist on this server, connected to the server, asked for the value, pulled that value, and then returned it. So you have no idea how fast these servers will reply, right? And the number of connections to each server also really matter, right? So that's basically it for the demo, guys. Kind of explained all this idea of Memcached. Let's go ahead and summarize this course. All right, we did the demo. Let's summarize. We talked about memory management. Memory is fragmented. If we didn't do the slab pages concept, then we're going to be allocating values left and right, right? And that, as a result, becomes fragmentation. And fragmentation is bad because now you have all these beautiful gaps of free space that we cannot use, unfortunately, right? Because our items might not necessarily fit these gaps, right? So we need memory management. LRU, again, a very unpopular opinion. I would like for this to be an option to be disabled so that I don't get locked, right? And keep my application simple. And if someone wants to build an RU, why don't they build it themselves, right? Or just have the client have the control. I wish they stayed simple and didn't implement this. That's just my only criticism of the Memcached. They stayed simple. They stayed to their rules. This is, in my opinion, I think it's an overkill, right? Threads, I love this design. Yeah, we can work with many threads, of course. There is a limit there is another problem with the threads design here, is that let's assume you have multiple threads, right? And each thread is a connection, right? Let's say about that, right? And when we looked at the data, I think when we looked at the stat, we saw that there is a fixed number of threads, right? And I don't know if Memcached share connections on a given thread, like have multiple connections on a thread. I don't know that. Maybe, because otherwise it's going to run out of threads, right? So in this case, what you can end up with is a thread with a connection that happened to have a very aggressive client, a client that sends a lot of data to this thread, you know? So in this particular thing, you create a bottleneck, and that bottleneck, really there is no solution to it because you don't know if a connection is going to be aggressive or lightweight, right? You can change that complete model to a centralized thread model, where is a central thread that takes the messages, these requests, and these requests will be distributed evenly, right? You can do that. but then the bottleneck is moved to a single thread. You lose either way, right? There is no solution, the best solution. That's when you go into deep these things. Like it's fascinating to me. I absolutely love it. We talked about read and write, talked about locking, covered distribution cache, which is completely client side. Guys, I hope you enjoyed this crash course, deep dive level into Memcached. Absolutely. I enjoyed researching this. Took me about a month to research this entire course. Absolutely love it. If you want to support the channel, become a member. There is a lot of member exclusive content in this channel. If you want to support otherwise, I have a lot of Udemy courses. There's discount coupons. Check them out, and that supports the channel. Appreciate you so much, and thank you all for your wonderful messages. Hope you enjoy this course. I'm gonna see you on the next one. You guys stay awesome. Goodbye.